we're not really covering any new content. We will just be doing a review of last semester. So I think most of you guys are familiar, but if you are new, this is a good lecture to get started with. So to start from the very beginning, right? Um, you may have heard the term AI, machine learning, and deep learning kind of used interchangeably, but they are related, but they have different definitions, right? So the broadest term is AI or artificial intelligence. So you could really call like a lot of different types of algorithms in AI, as long as its goal is to like be on par or surpass human intelligence, right? So like you could make the claim that all like graph search algorithms, like used in games or like kind of 80s, 90s arcade games, like you could call those an AI, right? Uh, like the CPU that you're playing against. So machine learning is a little bit more specific. So this is really any type of AI or algorithm that tries to use data to improve its performance, right? And so deep learning is a type of machine learning that uses a kind of building block called a neural network specifically. So again, the key here is that machine learning and deep learning both use data or a data set to improve performance over time, right? Deep learning uses a specific, like, I guess, tool called a neural network, right? And that's the difference between the two. AI is the broadest term. Okay. By the way, feel free to stop me for questions or if you have anything. I mean, there's really only three, four people. I think Pratik's heard this before. So, okay. So what is learning in general then? So in the in terms of machine learning, learning is defined as like finding patterns in existing data, right? So generally your workflow is that you might have a data set. So think kind of like an Excel sheet, like a spreadsheet, right? Where each row is a different data point, right? And so you have a model, some type of model that learns all the trends. That way, when you give it a new piece of data, like a new entry that you might collect, it'll able to predict a specific attribute. So for example, let's say we want to create a model that predicts housing prices, right? We might give it a data set that has, for each house, size, bedroom, and age, and again, we want to predict the sales price, right? So after our model, whatever the model is, learns all these trends in whatever large spreadsheet we give it, we can then give it a new house, right? And ask it to predict how much that house might cost. Does that make sense? Great. So what I just described is something called supervised learning, right? So supervised learning is when your input data, so again, the spreadsheet has a known outputs, right? So in the case that we want to predict sales prices, we know what the sales price is of each input data, right? So, and we call like these known outputs in the input data labels, right? So again, in our training data, right, in our data set, we have these labels and outputs. When we then want to do prediction, right, we give it something without that known output, right? Because we want to predict the label in our output set. Does that make sense? Okay. So within supervised learning, there's kind of two types. There's regression, where the output is any continuous numerical value, right? So again, the housing price example is an example of regression. You could also do something like rainfall, right? Weather prediction, where in rainfall you're predicting inches, right? So this is continuous, right? Yeah. So the other type of supervised learning is classification. So this is when you're outputting a discrete value where each value is mapped to a category. So for example, if you want to do, what type of weather is it? Is it uh, snowing? Is it raining? Or is it none? Right? So those are three categories, right? You might map the output of 0 to snow, 1 to rain, 2 to none, or something like that, right? Outputting a yes or no also falls under classification. We call this binary classification, right? So maybe the model outputs a 0 for no, 1 for yes, right? Okay, so those two types are supervised learning. A different type of learning is called unsupervised learning. So this is when, oh, let me move this guy. All right. This is when the input data does not have known outputs, right? So in this case, like we might just be given images and told to cluster them. But again, we don't like in our training data, we don't have labels to each of these images, right? So we can visually tell, hey, these are cats and dogs, right? But of course, like the model would have to kind of figure that out on its own. So as you can kind of maybe tell intuitively, unsupervised learning is way harder than supervised learning in a lot of cases, right? Because again, in supervised learning, the model is learning to map like kind of these input like these input features to outputs, while in unsupervised learning, it just has to, it doesn't even know what the output is so much, or it's doing clustering, but you're not really given the categories beforehand. Yeah, so this is kind of a table of kind of comparisons. Uh, for the most part, we've been covering, I mean, we've only covered supervised learning techniques and variations of that. Have any of you guys taken DSA 1 or DSA 2? Did you guys cover K nearest neighbors or KNNs? Oh, I see. Really? Okay. Uh, a very famous unsupervised learning technique is called K-nearest neighbors. You guys will probably learn them at some point. But essentially, unsupervised, you kind of usually think clustering. That's kind of the most famous problem. There are other different problems on unsupervised learning, but that's a very common one. Okay, so again, we'll be focusing on only supervised learning tasks. And again, within supervised learning, there's regression and classification. Okay, so again, we've kind of been talking about some model that does set tasks of supervised learning, right? So let's kind of think of our simplest model, right? So again, for example, let's say we want to actually implement that rainfall, I do make a rainfall model, right? Okay, so first question, is this supervised or unsupervised learning if we want to predict rainfall? Someone raise their hand and say it. Thanks, Emma. Okay, Emma's an officer, so next time it's you five that have to raise your hand and Pratik as well. You six. All right. Okay. So last semester, kind of the simplest model we covered was the perceptron, right? And so you might recognize these inputs as kind of the columns in our spreadsheet, right? So again, like if we're predicting rainfall, the humidity and temperature, right? I think I have to put one more, but so we call these columns features. So these are the categories like within our inputs, right? So each new sample, each new day, we're given its humidity and temperature, and based off these two factors, we predict the output, right? So these two factors are called features, terminology. Okay, so what a perceptron does is that for each input feature, it assigns a weight to it. So for example, in this case, we weigh the humidity with 0.5, we weigh temperature by minus 0.2, and so on and so forth. And so we then multiply that by these weights, take the sum, so 80 times 0.5, 25 times minus 0.2, and so on. We sum those products. We then add something called a bias, and then you can ignore this activation for now. For now, like we're not really doing anything with this activation, and then we output this final number, right? So again, it's a product, sum the products, and then add this term called the bias. So what are we actually doing here, right? So I just explained the mechanics. So weights basically what weights are they sorry, they're how much each feature contributes to the final output, right? So you can kind of see just by eyeballing this by hey, okay, so with a weight of 0.5, as humidity increases, you know, that with the positive weight, rainfall would increase as well. Does that make sense? And with temperature 25, since we have a negative weight, as temperature increases, rainfall would decrease, right? You can also see that, hey, like if you compare humidity and wind speed, humidity has a larger weight than wind speed. So that would mean that humidity has a larger impacts on the final output. Does that make sense? So you might ask, okay, why have biases in that case? Well, imagine that humidity, temperature, and wind speed were all zero, right? Then our output would always be zero. But does that make sense? Like just because the inputs are zero, does that always mean that the output should also be zero? So the bias is basically an additional parameter that is independent of the weights. So for example, maybe we're in a climate where there is always, 1 centimeter of rain, or sorry, 1 millimeter of rain, right? Regardless of what these three factors are, right? So that's why we have the bias. So again, the weights in the bias, these are numbers that we want to learn somehow. And I'll get to the learning part a lot later. But the point is, like, we somehow need to choose the correct weights and bias. And again, the activation isn't super important right now. What an activation is that it transforms the output through some function. So in this case, like the activation is like take the max between the input 36.5 and 0. So in this case, um, it doesn't really change the input. Okay, so we just did a regression, right? Well, how would we approach this problem if it was classification instead? So that is, let's say we want to say, will it rain? Yes or no, right? So no, output is 0, 1, it will rain, right? So in this case, we will use our activation, right? Because before we were just outputting number. In this case, we want to output a 0, 1. So again, we have our same weights and biases structure, but this time we pass it through this S function called sigmoid. So I know this might look a little bit hairy, but this is the graph of sigmoid, right? So you can see that if the input is less than 0, the number will be less than 0.5, the output. And if the input is greater than 0, then the output will be greater than 0.5, right? And it always maps any inputs, no matter what the input is, to a number between 0 and 1. So in other words, sigmoid always gives us a probability, which is pretty cool, right? So if let's say our input is 0, so right after adding the bias, we get a number of 0. Sigma would give us a 0.5, and that means like 50% confidence that it'll rain or not rain, which means we have no idea what this is, right? So output of 0.5 means like, we're not really sure what it is. So traditionally, right, after doing sigmoid, we get a number between 0 and 1. We then round that to get our final decision. So in this case, we get 0.182, round it down, and we get 0. Okay. Any questions about how perceptrons work thus far? All right, great. Okay, so again, perceptrons are super simple, right? Like you might notice that if we have a single feature, we kind of boil it down to y equals mx plus b, right? It's like this is just the equation of a line, right? So again, if our only factor is humidity, we do humidity times weight, so mx plus bias plus b equals y, our output, right? Again, in this case, we're not really doing much with the activation, so you could practically ignore that. So what does this mean? Well, perceptrons can only model linear relationships, as in they only really work when the input is linearly correlated with the output. So for example, let's say we go back to our three features. If temperature is 1, the output is 0.8. Temperature is 2, the output is 0.6, so on and so forth, right? So again, if we hold the other humidity and wind speed constant, right? We just fluctuate temperature. Again, the output fluctuates linearly, right? Like we could graph this and hey, it's a linear relationship between changing temperature and what the output is. And so, this is a pretty stupid model then, right? Because most, we want neural networks or whatever our model is to model any relationship possible, right? If it can only model linear relationships, I mean, most things in the world are not linear, right? So this is not super effective. How can we make this better? So before I continue, I'm just gonna like kind of restructure things like in terms of visuals. So I'm just gonna shrink everything in our perceptron into this gray dot. And so our new representation is that we have our three inputs, again, our three features, and those feed into our individual perceptron, and that's our output, right? So this and this are the same. Left and right are the same thing. Make sense? Okay. So we can take this, fairly stupid perceptron and then scale it up to something called a neural network, right? So the idea is that we feed our inputs to each individual perceptron, and then, well, when perceptrons are part of a neural network, we call them neurons, right? So we feed our inputs to multiple neurons, and these neurons feed into more neurons, which feed into more neurons, and so on and so forth, right? The hope is that by having this more complex structure, we can model nonlinear functions, right? So again, we still have our inputs, right? So we still have our three features from before. Each of these columns are called layers. And so these two columns are called our hidden layers, right? So again, each node here is a neuron, and inside each neuron is the same as perceptron. It's just we're just calling them different things now. So perceptrons send their stuff forward. So it's feed for you might hear the term feed forward a lot because they take their inputs and then send that to so this neuron would send its output, or its output would be the input to these two neurons, and so on and so forth. Does that make sense? Like we never send data backwards, and we, at least as of now, never send data like between neurons in the same layer. Okay, so I know this is a lot, right? But what this is really just saying is, again, let's say we have like a neural network for binary classification. In this case, we have one layer, like one hidden layer and one output layer. And so we have two neurons, right? In layer one, and then one neuron in the output layer, right? So here I just have like W11, W12 are the weights of our first neuron. B1 is the bias of that neuron, right? So again, I'm just like showing what the weights and biases are for each part. Okay, so again, if we kind of zoom in to this top neuron, the insides are the same as the perceptron, right? So again, weight is 0.5. Uh, the first weight is 0.5, the second weight is minus 0.5. That's what you see here, right? So again, we take those inputs, multiply weights, sum, add the bias, and then get the output, right? So now we are using this activation function. Now it's kind of important, right? So again, if you remember, the activation is just a function that transforms the post weights and biases operation, right? And so the activation is always, or you always want it to be, a nonlinear function, right? So as you can see, this function is called ReLU, right? So what it does is that it takes any inputs that are negative, maps those to zero. It doesn't change any positive outputs, right? So you can almost think of it as like turning off negative signals, right? And again, as you can see, this is nonlinear. If it was linear, this would just be a straight diagonal line. Okay. And again, I'll explain this a little bit later, but for now, just this nonlinearity helps the model learn more complex functions. Okay. So yeah. So again, if you were to do the math, 2 times 0.5 is 1, 2 times minus 0.5 is minus 1, so add those together. Uh, we get 0, add the by 0.75 out. So I don't have to do the math. Basically, here I've just kind of solved out all the intermediate values. Does that kind of make sense? Like, do you guys kind of understand how we've got here? And the out is basically the output of this neuron, right? The output is the output of this neuron, right? Okay. So again, when we in our layers, generally like all the neurons in the same layer have the same activation function, right? In this case, the output layer is has the activation of sigmoid, right? So generally, when we have activations in our hidden layers, right? The goal with these is to learn nonlinearity, right? By having by having these neurons with nonlinearity feed into other neurons, we can learn nonlinear functions. In the case of our output layer, though, we don't really need to do that. In this case, we put the sigmoid activation function to, again, do that mapping between 0 and 1, right? So the sigmoid just formats our input to 0.32, right? A nice number that's between 0 and 1, a probability. Okay, so it turns out that if we still had this neural network structure, right, and just took out the activation functions, right, what we find out is that our entire neural network gets reduced to a perceptron mathematically, right? Which is pretty interesting. So with the activations, we can actually learn nonlinear functions, right? Again, without activations, a large, massive neural network can be reduced, like can be provably reduced down to a perceptron, right? So again, we need those nonlinear activation functions. Okay. So we went over sigmoid, which we usually use at the end to format our outputs, but you could use them as intermediates, just like ReLU. We went over ReLU, which is kind of that max function. There are a ton of other activation functions. Like this isn't even all, like there's a ton of activation functions. I don't really have too much time to get into them now, but basically, if you ever see activations with this kind of plateau behavior at either ends, you generally want to, not always, but sometimes avoid using them in your hidden layers. Those can cause a lot of problems later on. Generally, ReLU and its variants are a lot more friendly. Okay, if you guys remember, these two cause vanishing gradients from last semester. Question.
I know Value sometimes has the problem where like if the nodes die off too early on in the
Yeah,
network, like you just end up getting a bunch of
exactly,
zeros
exactly,
throughout. That's what leaking value is supposed to fix, or
exactly. Yeah, yeah, exactly. What's your name?
I'm Leo.
Leo. So what Leo is bringing up is that let's say in our neural network, the inputs to both these neurons maybe we're lucky we choose bad weights, right? Um, they're always negative, right? So the input to our ReLUs, if they're always negative, we always output zero. If we always output zero, then well, we can't really do anything, right? So remember, we do multiplying weights is a large step. Anything multiplied by zero is zero, right? So leaky ReLU So again, if too many of our numbers are negative, ReLU would cause them all to be zero, effectively kind of crippling our neural network. Leaky ReLU aims to kind of fix that. Okay. Um, yeah. So again, we just kind of covered, thus far we've covered regression with neural networks and binary classification. What if we wanted to do multi-class classification, right? So not just outputting a 0, 1, but multiple classes, right? How would we do that? So in this case, there's a lot of text here. Um, Instead of having a single output neuron like we did before, we have one output neuron for each of our categories, right? So again, if we're outputting like the weather, we have one for snow, one for rain, and one for none, right? So what we then do is take each of these raw outputs. So we call these raw outputs of our model logits, right? Just more terminology, right? And again, when I say raw outputs, I mean all we did is multiply them by weights and biases. And that's really it. We haven't done any activation stuff yet. So generally, when we're doing multi-class classification, we always use the softmax activation function. Just as sigmoid helps us format our outputs for binary classification, softmax does the exact same thing, formatting our outputs into probabilities, just for multi-class classification. Does that make sense? Okay. So I know this looks kind of funny, but if you ignore this E term, we have each Z, so Z being each of our logits, so Z1, Z2, Z3. We have each of our Z terms divided by the sum of all the Z's. In other words, we're getting a percentage, right? So for example, 3 over the absolute value of 3 plus 1 plus 1 plus 1, right? So 3 over 5, right? So notice I said absolute value. The nice thing about softmax is that it does two things. One, it makes all of these e to any number is positive, right? So it handles these negative numbers, right? So that way, again, we can get that nice percentage that we had before with sigmoid. The other thing is that raising e to that number exaggerates differences, right? So notice that, these three numbers aren't that far apart, if that makes sense, right? There's a difference of 2 between 1 and 3, difference of 2 between 1 and minus 1. Whereas after we do our softmax, there's a very large difference, right? So softmax has those two functions. We then do something called an argmax, which is just a fancy way of saying take like the index, if you guys have covered arrays, take the index with the highest number. That's it, right? So in this case, 0.867 is the highest number. We take the 0th index. Class 0 is our output. In other words, our model output a class of snow. Does that make sense? All right, perfect. Okay, I don't think we have to do too much review. So thus far, we kind of, we've been working with weights and biases, but we haven't explained how we actually get said weights and biases, right? Right now, I've just kind of chosen them. But in reality, your neural networks are very deep, they're very large. You might have hundreds and hundreds, if not millions, of weights and biases, right? You can't manually choose each one. So training is a process of iteratively learning which weights and biases are best suited for your problem, right? So you start by randomly choosing your weights and biases. And then for each data point, and again, this is the very rough vanilla algorithm. Later on, we'll cover more um, like better variations of this. So, but for now, for each data point in your spreadsheet, right, we do something called a forward pass, which is what we've just did. It's setting those input features through our neural network and calculating an error. Backward pass is the process of actually calculating how much each weight and bias contributed to the error, and then using that error term to update, right? So forward pass is just chucking stuff through, see how badly we did. Backward pass is correcting things. Okay. So again, another visual change. Um, so in this case, we're working with a super simple neural network, if it could even be called that. Um, so, we have two layers, but this time, like our layers only have one neuron, right? So there's no, I guess, width to our neural networks. There's two layers deep. And so I've just kind of visualized them more simply here, right? And again, we're using a single ReLU activation. So one hidden layer, this is effectively our output node. Okay, so as you can see, right, after passing everything through, we got an output of 1.8. Let's say our true output was the number 3, right? So we can get creative in terms of how we quantify our error, right? So generally, the term loss is what we call our error term, right? So again, it's how well or really how bad our model did, right? And so generally, however you choose to define your loss function, it always has to be positive. That's the main criteria. And a loss of zero means that we have zero error. Those are really the two criterion for having a loss function. Now, from there you can really choose whatever you want, right? These are two very common loss functions, mean squared error. So in this case, we had 1.8 as our output. So sorry, as our y predicted, and then our y true was 3, right? So it's subtracting the difference, like, our, I guess, direct error, how badly we did, and squaring that. Mean absolute error is just taking the difference between our prediction and the truth, but taking the absolute value, right? And there are a ton more loss functions than this. These two, or at least mean squared error, is probably one of the most common ones you'll ever see. Okay. So again, forward pass, I mean, we've already seen how to send data through a neural network, right? Um, we then calculate, the key here though is calculating the loss from this, right? So 1.44. This is kind of semantics, but I guess sometimes it's considered that calculating the loss is part of the backward pass, but that doesn't really matter. Okay, so now the key here is that we want to use this loss to improve our weights and biases, because right now we've just randomly chosen them. So the backward pass has something, the kind of the backbone of the backward pass is called backpropagation, right? So this is calculating how much each parameter contributes to the loss. Once we know each parameter's contribution, we can then update really simply, right? So for example, right, or really we want to solve for individually for W1, B1, W2, B2, like for each one, we want to numerically quantify how much it contributed to the loss. Okay, so gradient descent is that process, right? So for each data points, yeah, okay, this helps us do that. So this is kind of a common visual you'll see a lot when talking about gradient descent. So on the x-axis, I have the value for W2. On the y-axis, I have the loss, right? So we never really have access to this plot. This is more of a theoretical plot, right? So you can imagine that if we have a dial on W2, right, decreasing it, increasing it, you can imagine that, hey, like different values of W2 would treat the loss or would impact the loss in different ways, right? So since we want to minimize loss being our error, we want to find this value of W2 that brings loss to a minimum, right? Not a local minimum, right? Because, but a global minimum, right? So the way we do that is by calculating the gradients. If you have taken multivar Calc 3, you should know what a gradient is. If not, it's effectively our derivative, right? So again, um, yeah. Okay. And so once we have the derivative of how our individual parameter contributes to the loss, we can move in the opposite direction. So in this case, W2 would have a positive derivative here, right? So by moving in the opposite direction, down, that brings us to a lower loss, right? Because the derivative tells us the relationship between W2 and loss. Derivative is positive, that means increases W2, increases the loss. Any questions about this? And I'm kind of skimming over gradient descent. So we'll go over an example of how to actually calculate these derivatives in a little bit. But yeah, okay. So for each individual parameter, we can pretty easily, at least with modern software, calculate these gradients. So really now in like with Python, if you've ever heard of PyTorch or TensorFlow, these automatically calculate the gradients for you, right? Yeah. So, okay. And so the learning rate, so yeah, so what you would normally do is that you would take the original weights and subtract the derivative. Oftentimes the derivatives tend to be really big, so you don't want to take too much of a jump in either direction. So the learning rate scales down these partial derivatives. So for example, um, if our weight for W2, what is it? Uh, if it's 0.8, right? And our derivative happens to be like minus 10, right? We don't want to just like, or sorry, if our negative gradient happens to be minus 10, we don't just want to like, change 0.8 and then subtract 10 for that, right? That would really skew our weights. The learning rate scales that down to a more manageable number. So instead of minus 10, it would scale it down to maybe like minus 0.0001, right? So again, the learning rate is not learned. It's a parameter that we set before training. And all of our negative gradients are multiplied by the same learning rate. Okay. Yeah. So as we kind of said earlier, loss by that's forward and backward propagation. Does anyone have any questions? Okay, we'll work through an example in a little bit. Okay, so just before we do that though, loss, as we've covered, is not the best metric because again, for different problems, we could use different loss functions, right? Mean squared error and mean absolute error are pretty, easy to intuit, right? But, there are tons of different loss functions. Oftentimes, they're not the best metric, right? Especially to an outsider looking into someone else's work. So accuracy is usually the go-to in classification problems. So it's really just the number of correct predictions over the total number of predictions, right? So all these are for classification, by the way. Yeah, so recall is another metric. So it's the true positive predictions out of all total positive samples. Precision is the proportion of true positives over like all positive predictions, right? And there are a ton more metrics than this, but these three are the most common you'll probably see for classification. Okay, so let's actually go through an example of forward and backwards propagation. So in this case, our input is 2. So the output of this blue, right where we are here, is our input x times 0.5 plus 1. So that gives us a output of 2. We then put this intermediary value z1 through our array loop, and we get a positive 2 output. By the way, I'm kind of giving variables for intermediate outputs for now. It'll be clear in a little bit as to why I'm doing this. But yeah, just for now, I'm just assigning these to intermediate variables. So yeah, again, this z term is the output of the weights and biases operation. The a term is the output of the activation function, and then finally we get our y prediction, right? Which is just multiplying this activation term or the output of the activation times the weight plus a bias. Okay, so we then do our loss function, right? Which gives us 0.72. In this case, again, I'm using a variation of mean squared error. Instead of just squaring the difference, I'm taking 1/2 of that. Honestly, this is not really a common thing. I just did that so the next steps will be easier. Again, loss functions don't really, they can almost be arbitrary. So in this case, there's nothing really wrong with tweaking your loss function however much you want. As long as it's positive and as long as 0 means uh, an error of 0. Okay, so we just did our forward pass. We got a y prediction 1.8. Our tree output is 3. Backward pass is, let's say we want to calculate that negative derivative, right, of W2. How would we do that? Well, remember, we've kind of saved all of our intermediary values during our forward pass, right? So what is a derivative? Like, I'm sorry. What we want is the derivative of the loss, right, relative to W2. In other words, this partial derivative term, if you're taking multivar, this should be very common terminology. If not, this is just saying the derivative of the loss with respect to W2. In other words, how does W2 impact the loss? So again, W2 doesn't really come into play in our long chain of equations until the latter half, right? So if we wanted to calculate the loss, we just do a chain rule, right? Which again should be familiar from calculus, right? So if not, the chain rule is basically saying, since we kind of have these two functions here, the derivative with respect to W2 is equal to the derivative with respect to y pred. In other words, our first intermediary output times y pred with respect to W2, right? So again, if you just do the math, we get that minus 1.2 derivative, right? So again, as you can see, the magnitude of 1.2 is pretty large. If you were to just directly subtract this to 0.8, we would probably skew our model a lot more than we want to. So instead, we multiply that by this learning rate. In this case, we said 0.1. That significantly scales down how much we update our weight by. And now we get a weight of 0.824, right? So 0.24 or 0.024 off from what we started with, right? And again, this is iterative, right? So this is one pass of backpropagation. We then would do forward propagation again, right? And then backward propagation again, so on and so forth, right? Okay. So I won't fully go through how it works for like the W1. It's basically the same thing. The difference is, the further back you are in our chain of calculations, like you are in W1, the longer this chain rule becomes. Does that make sense? Any questions about our calculations or anything like that? All right, perfect. Then I'll just skip to that, blah, blah, blah. All right. So again, most deep learning is done in PyTorch. Before it was kind of done in MATLAB, I think. Some of the alternatives are R, and all of our deep learning like libraries, so PyTorch and TensorFlow are the most common. The wrappers for like C++ stuff, or sorry, C or C++ stuff, right? So generally we do deep learning. It's easy to do it in Python, but you might see some stuff in C or C++. If you've ever heard of GPUs, all of that work is mostly done in C and C++. R is more for statistical analysis. Generally, Python gives you the most functionality. Um, yeah. So yeah, I won't cover this too much, but just know that in future lectures or just in our projects, we will be covering PyTorch and stuff like that. Okay. Um, Before I do that, before I keep going, we have time. We'll do a Kahoot. So Kyle suggested we do Kahoots last semester, which was a very good idea. So we will do those now. So this will be a review of the first set of slides that we've done. Um, I don't know. We don't have shirts yet, but I was thinking like this is up to Seth, but maybe keeping track of like who has a wins the most Kahoots and they get like a free shirt or something. I don't know. That might be fun. We don't have shirts yet, but we'll have shirts eventually, I promise. Fingers crossed. All right, officers, you guys can do it. You guys, yeah, you guys are gonna skew the score. I mean, you guys can, but like if you get anything wrong, I'm gonna like be very disappointed.
Yeah, I'm too scared. It's bad. So,
Tank the scores.
better than my ability.
And if you win, you guys don't get a free shirt. So too bad. No. When did they come up with these weird icons? Huh. Was everyone able to scan in? All right. I'm gonna start. Okay, I'm gonna start. What the? All right. Rafi better win then. Okay. Oh, by the way, I don't think I introduced myself. My name's Rafi. Nice to meet you all who are new. Okay. Oh, I don't have the cute music. It's not playing the music. I don't know. It's very distressing. Oh, there it is. Oh, my bad. Yeah, 10 seconds for each one. It goes faster that way. All right. I think some people may have not gotten the chance to answer because this thing was blocking it, so it's my bad. But I think, is anyone confused on this question? You good? All right, perfect. Okay. Now I have to put this guy in the middle. How do I just get it? Oh well, it's here. 10 seconds is pretty fun because you guys, it's more intense. All right. So the clustering was referred to unsupervised learning. So again, supervised learning is like all it boils down to is that in our data set, for each input, we know what the output is. So our model is learning to map inputs to outputs. Unsupervised learning is when we don't have any outputs. And so clustering is when we have a bunch of inputs and the model somehow figures out how to group them together without any given labels. Okay. How do I keep going? Oh, there it is. All right. Wow, Shazab. All right. Nice, nice. Also, I'm in second place. Yeah, what's an example of regression? This one should be easy because I kind of use it as an example. Yeah, everyone got that one out. Okay. Um, Shazab, since you're in first place, what would you call like what is this red one like classified as? Yes, very precise. Uh, okay, wow. It's pretty close. Oh, okay. I thought it was 201. I got very distressed. Yeah, what's the difference between classification and regression? Sorry, classification and regression difference. Yeah, okay, most people got that right. So I know I went kind of fast with things. Classification and regression are just types of problems, right? So those supervised, unsupervised things, they apply to just all of deep learning. So be it perceptron, neural networks, any other type of model. I know I kind of cover them in the context of perceptrons, but again, these are just problem definitions, right? They're kind of independent of whatever model you choose to use. Yeah, so classification outputs certain categories. It doesn't like what model you choose doesn't really matter, right? It just, you know, it's a problem definition, which is independent to the model. Dang, rankings change, but Shazade still in the lead by too much. I don't know. I don't know how relative Kahoot rankings are. I feel like these are pretty small margins. Why do perceptrons suffer? Okay, that was a typo from me. Green is not right. The first of hopefully the only error. Last time I did Kahoot, it had like a ton of errors. Okay. Fortunately, no one chose this, so no harm was done. Yellow is the only correct answer. All right, no change in ranking. Wow. So I think there's 3 more questions, or inclusive 3. Yeah, so we haven't actually covered what normalization is. So right now it should be, if you haven't learned it yet, it's kind of a gibberish term. We'll cover normalization in the second half of the lecture. No. You could no, I mean, oh, I see what you're saying.
I don't think
You
we
would-
ever normalize the input data, though. Like it would.
You normalize the output data.
Intermediate, values. But it would
Sort
never
of, yeah.
normalize inputs.
Yeah. So sigmoid normalizes the output data, not the input data. Okay. It's to introduce nonlinearity, which just means it's really any function that's not linear. That's not a line. What is the name of this said nonlinear function? Hoping to have the most states in this. All right. Softmax is the binary classification activation function you use. So softmax and sigmoid, like sigmoid is the one that looks like an S, maps things to 0 and 1. Softmax does something very similar, but it operates on multiple inputs. So softmax converts things to probabilities, but just multiple inputs. ReLU is the max. Oh wow, there's a little bit of a changing. Wait, who's Rafi? Whoever is Rafi needs to be first place. Otherwise, I'll be very disappointed. Wait, what question? Okay, so 2 more questions before we get back to the lecture. I just said the answer to this. All right, and I think I messed up. All right. This is my bad. Okay,
Goodness.
yeah, okay, so softmax and sigmoid are both the right answer. All right, so the last couple questions will be double or nothing questions, so you can get the points back.
Yeah.
Okay, I forgot. That's my bad. All right, I might have to invalidate this Kahoot then. T-shirt competition. That was a pretty bad mess up. All right. All right. Okay, this one's fully correct though. So I know I said it could technically be considered, but yellow was the best answer. It's to compute the gradients of weights and biases. That's back propagation, right? Computing predictions is forward propagation. All right. Well, hey, if it matters, okay, I think the second last question tanked Rafi, but I think oh, wait, did you also get Yusha save? Never mind. All right. Irreparable damage has been done. All right, so back to the lecture so you can forget my mess up. Okay. All right, I'll try to blaze through this. So what we've covered is kind of like the vanilla neural network, right? So that's really it. Now, if you were to go in the wild and use it, it would fail on most problems, right? So first is how we're using gradient descent. So what we've been doing, where we calculate the gradient for each individual input that passes through our neural network, this is called stochastic gradient descent. So again, this is what we've been doing. So I know we have a lot of graphics here, right? So just imagine we have 15 data points and we have a couple of outliers, as you can see, or sorry, three outliers down here. Because we're calculating the gradients for every single input, that means 15 updates, right? It's a lot of updates. Um, the problem though is that each of these updates are treated the same. So these outliers, so when I say outlier, I mean inputs that aren't used, like that the model really should ignore, right? Obviously, we can't hand label inputs in large data sets, but we would hope that the model will be robust enough to ignore outliers, right? Fortunately, with stochastic gradient descent, it doesn't do that, right? So the impact is that obviously we update very quickly because each update only requires one input. The problem is that outliers can push our model in the wrong direction. The reason why it's called stochastic as opposed to deterministic is because the order in which your data is organized matters. So for example, if you were to randomly shuffle, right, which inputs update the model first, we would get a different model, right? So with stochastic gradient descent, we generally, for each time we pass through the entire data set, it's called an epoch, by the way, like one pass through the data set is called an epoch, right? So in this case, we have 15 updates per epoch. If we were to shuffle or updates, we'd get a different neural network at the end of each epoch. So generally, between epochs, we shuffle our data set and then go through it again. This isn't to say stochastic gradient descent is like bad all the time. It's still very usable. Generally, though, as we scale things up, we don't want to use it. So batch gradient descent tries to solve like a lot more of these problems. So in this case, when we have 15 points in our data set, we only have one update. So what we do is that we average out all of the data in our epoch, or sorry, in our data set, right? So if our data set is 1 million samples long, right? We average all those gradients, that's one update, right? So as you can imagine, that's very slow, right? Because each update relies on the entire data set instead of one sample. The pro, though, is that it's very stable and it's not stochastic, it's deterministic, right? Because we're taking an average. It doesn't matter how things in our data set are arranged, right? Because we're just averaging all of them and then subtracting that. Obviously, you also need a lot of memory because you're not just storing the gradients, you're storing the intermediate values for everything and so on and so forth. With stochastic gradient descent, you just need to store the intermediate values for one pass through and then forget about them because your next update is with a new data point. Okay, so mini batch gradient descent is kind of like the in-between. Instead of taking the average of the gradients from our entire data set, we instead, at the beginning of each epoch, randomly group our samples. So in this case, we randomly group them to groups of 5. And then within our groups, we take the averages of our gradients, right? So again, it's a lot more stable. Obviously, the smaller your batches are, the less stable it becomes, right? So yeah, when I say how do we choose batches, I mean like how do we choose like the constants of each batch? The batch size is generally fixed at the beginning, like before training. Okay, so Adam kind of breaks away from these three. So there's a lot of different types of things called optimizers, which are significant improvements onto our gradient descent, right? So thus far, like these three variations, stochastic gradient descent, batch, and mini batch, all of these are still just doing gradient descent as normal, right? You're just doing something called batching. Adam is an optimizer. So we are doing something similar to gradient descent, but we are changing the mechanics. So I don't have time to get through everything, but optimizers are kind of a family that replaces gradient descent. So you can do batches on like batching on top of optimizers. And again, it operates to a very similar principle. It just improved. Yeah. Okay. So on to some problems. Two super famous problems when dealing with any kind of machine learning problem is called overfitting and underfitting. So overfitting is when we effectively memorize our training data, right? So that means we end up learning those noise and outliers, right? So why is this bad, right? Because we've precisely learned our input. Shouldn't this be a good thing? Well, the problem is that our training data is a sample of the larger population using statistical terms. For example, if you want to model how sleep impacts grades, right? And we only interview people in this room, would that be a good sample? I mean, we're all probably mostly engineering majors, most of us CS majors. I mean, it's a lot of confounding factors here, right? The problem with this though is if this is our only piece of data, right? This is all we have to train on. Our model could memorize all the different, you know, trends that are specific to our sample, not to the larger population. So, when we then sample something from the population as opposed to our trained data, we then have a lot of errors. Does that make sense? So overfitting is when we memorize like the unique trends in our sample instead of like the larger trends we do want to memorize. Or sorry, remember. This happens if we train for too long and if our model is too large. Underfitting is the opposite problem. It just fails to really learn any significant patterns in the data, right? So this could be if we don't train for long enough, right? Our models, our weights or bias are still in that randomly initialized zone, or if our model is just too small or too simple. So some neural networks, like if they're small, like think of a perceptron, right? Perceptrons can't learn nonlinear functions. Similarly, small neural networks are kind of capped by their complexity, right? Too small of a neural network, you can't learn complex functions, but too large of a neural network, you end up memorizing kind of the useless stuff in your data set. You overfit, right? So it's a very difficult optimization problem that you have to choose between. So a lot of the specialized neural networks we've covered, and I'm going to cover in a little bit, CNNs, RNNs, so on and so forth, they kind of add a bunch of building blocks to our base neural network to kind of address a lot of these problems. So again, traditionally though, like we split our data into two parts, training and testing. This way we can better identify if we're having underfitting or overfitting. So again, like if we reserve 80% of our data for just to train with, we might reserve the remaining 20% not to train with, but to test with, to get an objective view of how our model does on data it hasn't trained on, right? So if our model is very good on the trained data, but it's really bad on performance, we have overfitting. If it's very bad on both, then we've underfit, which means we haven't learned any kind of trend. Okay, so I'm kind of short on time, so I'm kind of blaze through this stuff. So regularization is kind of a family of techniques that combats overfitting, right? So these techniques, they might modify the model or they may modify the loss function. So L1 and L2 losses, as the name implies, they are addition to the loss function. So for example, you might do mean squared error, but then add this additional L1 or L2 term, right? So the L1 term is the sum of the absolute values of all your weights. The L2 term is the sum of um, it's the sum of all the, sorry, it's the square root of the summed squares of your weights, right? So the effect is that we're effectively, remember, the loss is our error, right? It's our penalty for our model. So by including these L1 and L2 terms, we're penalizing the model for having weights of like that are large, right?
Mhm.
So obviously, like if all of our weights are like, 10, 20, 30, so on and so forth, this term will dominate the mean squared error term and will really punish the model for having large weights, thereby bringing them down. So the L1 term is very aggressive. It sends a lot of your useless weights. So let's say you have a very deep neural network, a lot of your weights and biases are useless, right? L1, the hope with it at least, the goal is that it sends those useless ones straight to zero, right? L2 is instead of sending things straight to zero, it just kind of keeps them low, right? That's all it really does. So dropout, this impacts the model kind of on more architectural level. If we have a very deep neural network, each epoch, we randomly choose neurons in each layer to turn off. When I say turn off, I mean their outputs will be mapped to zero during that epoch, right? So what does that mean if we map the outputs to zero? That means that the forward layers can't use those neurons. And because their outputs are always zero, what is the gradient of zero? Zero, right? So we're not doing any backpropagation on these turned off neurons for that one epoch, right? So we randomly choose neurons to turn off. And the goal is that for each epoch, neurons that aren't turned off learn to use each other as opposed to being really reliant on one or two neurons. Okay. Generally, dropout is super aggressive, as is L1. L2 is usually the safe bet. Of course, for specialized problems, you might use either one. Okay. So another super big thing, more important than regularization, is normalization, right? So there's a lot of aspects to normalization. In this case, you always, no matter what the problem is, normalize your input data, right? So for example, if our inputs are squared footage in predicted or in bedrooms, right? The scale of the number of bedrooms will be like what, 1 through 10. While as oh, this is gonna turn off. God, I hope it doesn't turn off. Okay. It turned off. All right, I'm just gonna no. It just turned off the stupid thing. All right. You guys, okay, bedrooms and square footage, right? You guys remember those, right? So you can intuit that bedrooms, what? The range is 1 through 10. Square footage, what? Like that, we're maybe talking thousands or tens of thousands. If you're really rich, hundreds of thousands, right? So because the magnitudes are so different, um, remember weights kind of quantify the importance of a feature, right? Way back from when we were talking about perceptrons, right? Obviously, if our weights turn on. If our weights are, of similar magnitude, right? But the inputs are really big. Let's say like the weight for the room number or for the room feature and the weight for the space feature are the same, right? Well, obviously the space feature, because the inputs are just way bigger, this will end up dominating like will contributing a lot more to the output. So it'll like the model will end up focusing way more on the bigger number, right? An easy fix to this is normalizing, right? So essentially, this just if you take statistics, we just take the z-score of all of our input features. What this effectively does is it brings everything down to the same rough range. So instead of like magnitudes of this being a magnitude of 1,000, this being like ones and tens, brings everything roughly to not the same exact range, but roughly brings them closer together. Does that make sense? Okay, so you can take, so right now we're just normalizing the inputs. You can also normalize the intermediary values in our neural network. So you could also normalize the output of each layer, right? So there's two types or two traditional types. There are a lot more than this, but these are kind of the classic ones. There's batch norm and layer norm. So batch norm normalizes each feature relative to single inputs. Layer norm normalizes all the features for the same input for the single neuron, right? So I know that's a lot, but basically, from these two techniques, what's useful to remember at this point is that batch norm, as the term implies, is it dependent on the batch, right? So with different batch sizes, you get different behaviors. Oftentimes, it's not desirable, right? Because we're just adding another confounding factor to how our model performs. Layer norm, because it normalizes across like a layer, right? And again, our layer is always constant, right? Unlike our batch, which is a hyperparameter. Layer norm is independent to that problem, right? So more recent architectures use layer norm as opposed to batch norm. Batch norm still works fairly well though. Okay, so I'm going to go through this super quickly. So far we just talked about neural networks and some ways to improve them. So now I'm going to go through like the specialized models we've covered, really just what they are and when to use them, right? So the first that we covered last semester was CNNs, convolutional neural networks. So if you remember, the example I've been using for neural networks is like a line in your spreadsheet, right? That's because neural networks, they can only take like a 1D array, if that makes sense, right? Because your features, you can't really have two-dimensional features. How would that work, right? There's no such thing as a two-dimensional way. So convolutional neural networks accept two-dimensional input. That's kind of the big innovation. So traditionally, what's a very common two-dimensional input? Images. So whenever you're really working with images, specifically classification, we would use a CNN. Yeah. So this orange part are CNN specific things. The output of this max pooling layer is that 1D vector, right? And then we use our classic neural network, output layer. The blue stuff is what we've seen before. So the key here is, and this is a very common theme in machine learning or deep learning, we often do a lot of pre-processing to our inputs to make it easier for a neural network to learn, right? So what CNNs kind of tell us is that chucking this input directly into our dense layer, let's say we were able to flatten it down somehow, right? That would perform worse compared to the set of pre-processing steps. So RNNs kind of go by a similar principle. So RNNs handle sequential data. So inputs have a distinct order. Think maybe like the prices of stocks day by day, or like words in a sentence, right? In this case, the order of your inputs matter. So yeah, so sorry. The problem with RNNs naively, like the base model, is that they forget input that happened early on in the sequence. More common sequential models are LSTMs and GRUs. So these are still based off of RNNs. They just don't suffer the long-term memory loss as much. Does anyone know a other sequential model that is more robust than these two? Just raise your hand and say it. Or just say it out loud. Transformers, yeah. That's GPT, that's ChatGPT. We'll be covering those in the coming weeks. We haven't covered those yesterday. Transformers kind of blow all these out of the water. But yeah, we'll get to that later. So autoencoders are kind of different from that. So autoencoders, so these two, CNNs and RNNs, they're still doing your classic regression or classification problems, right? CNNs, traditional classification, RNNs, either one, right? Now with autoencoders, we get into kind of a different territory. Autoencoders, their function is to transform your input into whatever you want, right? So in this case, we have a deblurring autoencoder. We take a blurry input image, and the goal is to unblur it, right? So think transformation, right? So like, yeah, literally transformation. So autoencoders have two kind of structures, like a funnel and then the other end of a funnel, right? So encoders are literally like a neural network that gets smaller and smaller and smaller, right? The idea is that you take this original input and you crunch it down to something called a latent representation. And the decoder takes this reduced, crunched down latent representation and tries to blow it back up into an output, right? So the reason why we do this crunching part is that it forces the model to extract only relevant pieces of data, if that makes sense, right? So we're just extracting the bare bones of what we need and then using that to output our transformed image.
Is the encoder portion similar to how like in CNNs you're dotting each
Yes,
region
yes.
of the image with like some feature detector sort of matrix?
Exactly. So in the structure of an encoder would look very similar to this orange part. Like it looks very similar to this portion of a neural network, or sorry, of a convolutional neural network without the blue stuff. Yeah, exactly. Decoders are kind of or at least in this case, would be the reverse of a CNN, if that makes sense. I guess it wouldn't, but it kind of blows up. Just CNNs kind of crunch down information before sending it to the neural network. The decoder would do the opposite of that, as in blow the image back up to its original resolution, but transform. So variational autoencoder, with variational autoencoders, we go into the realm of generative stuff, like generating images, right? So there's a lot of stuff to cover, but basically what variational autoencoders do is that we take our encoder and we learn all the different ways to summarize an image, right? Like we would with an autoencoder. The difference of variational autoencoders, though, is that they kind of crunch down information a little bit differently. So that way, if we want to generate a new image, we can just pick this latent representation, like let's say a random one or a new one, and then generate a new image from that, if that makes sense. So for example, if we know 67.27 is the latent representation for the number 5, if we want a new number 5, we could just fluctuate, like change the latent representation a little bit and generate a new image of what we want. In practice, though, variational autoencoders, they're very easy to train, but they have kind of crappy performance. They're not super good. Generative adversarial networks are the opposite. They used to be the state of the art, and they still work very well. But they are notoriously hard to train. But if they do work, they work very, very well, right? GANs have two models, like two, not independent, but two separate models that train together. So you have a generator, which looks like the decoder of your um, autoencoder, right? Essentially, you take a small vector and you blow that up into an image. The discriminator is literally a CNN in this case. It just classifies if an image is real or fake. So the goal is that we want to generate these two train in tandem. The goal is for the generator to fool the discriminator, if that makes sense. Once a discriminator can no longer tell the difference between what's real and what's fake, fake being generated, real being from the data set, that means we have a generator that can realistically produce images.
Is the discriminator being trained at the same time?
Yeah, so you can think that the generator like outputs a few images, stops training, then the discriminator reviews all the images, sends that data to the generator. Like they take turns training, basically. So the generator outputs a bunch of images. The discriminator outputs real or fake. That real or fake assessment is sent to the generator to train on. If that makes
So,
sense.
so like the generator will produce its images, the discriminator will get good at telling the difference between what's real and fake, and then it'll go back to the generator, which will try to fool it again.
Exactly, exactly. As you kind of see, this back and forth mechanic can get really like annoying and hard to train.
So it's not a frozen CNN, it's training, like,
Yeah, so when one is, sorry, continue.
yeah, like it trains it like again and again, and then it goes back to generator, and then it trains between that and the CNN. It's not just a frozen CNN that's already had like.
No.
Okay.
Yeah, the very important point to make. Yeah. So the discriminator is not a pre-trained CNN. We actually don't want to use that. These two learn in tandem. If you have questions about this, I can cover at the end. But it's essential that these two learn together. Again, this is very hard to train, but when it works, it's state of the art. Diffusion models, I didn't the architecture is a lot, so I didn't put it here. But essentially, well, the architecture looks like a autoencoder, but that's not really important. The important part is the way it works. So the idea is that diffusion models, instead of sampling like a latent vector like autoencoders and GANs do, they start with noise and learn to subtract noise. So almost imagine like a stone, like a block of stone, right? That just being like noise. Diffusion models learn to subtract noise, so kind of chip away at the noise to produce an image that we want. So yeah, these are kind of like VAEs, they're very easy to train. But like GANs, they perform very, very well. Okay. So that's it. I went a little bit over time. If you guys have to leave, obviously leave. If you have a few minutes to stay, I'll keep going through the Kahoot and then we could do questions. Now is a good time to leave. You have to leave. Thank you for coming to today's lecture. If this is your first time here, my name's Rafi. I used to be the main lecturer, but today's probably going to be one of my few lectures given this semester. Shubes will be giving the next lecture next semester. Then it'll go back to Seth, our lecture lead for this semester. I'm just kind of, starting you guys off, I guess. All right, back to the Kahoot. If you need to leave, leave now. If you have any questions, by the way, in our Discord, we do have a lectures channel. Feel free to post questions there. It's not a big deal. Okay. These are all double points, by the way, so yeah. I don't think anyone's doing the Kahoot. All right. Oh, you are. Is anyone doing the Kahoot? No, I can just pause it now and just do questions. 4 people are. Do you guys want to keep going through the Kahoot or just like break it here? Yeah, we said here. So I kind of went overtime. It took me a little bit of time to set up, but generally lectures are just an hour long. I tried cramming a bunch of stuff in, but okay. Yeah. Yeah, this was meant, I think some of you guys are new, but if you need an actual intro, I recommend going through our slides from last semester. They're on our website at ml@uva.org on lectures, and you can just kind of flip through them. I tried to give you guys like a super quick overview. Most of today's lecture covered the first 3 because that's kind of the fundamentals that it's essential you guys know. After the first 2, we cover more specialized stuff. Okay, any questions?
Like that CNN's lecture, will it be like just like a
Just
deep
CNNs.
dive?
Exactly.
Yeah, next week, I think like the next 3 weeks, we're gonna be learning transformers and natural language processing. So we're gonna go all the way from like, how do you represent words, vectors, into like, how does ChatGPT work? How do all like modern LLMs work today? So that'll be fun. I think I'm gonna do the first one.